In the world of AI, we are constantly working with data that has multiple dimensions. Images have width, height, and color channels. Videos add time. Point clouds combine spatial coordinates with features. This rich, structured data is everywhere. So here's the question. Why do neural networks flatten the data they want to learn from? Let's compare the traditional approach with our solution. NdLinear. Traditional linear layers flatten rich data into a single vector. This forces the model to relearn spatial relationships, and it creates massive parameter overhead. NdLinear processes each dimension separately, preserving the original structure and dramatically reducing parameters. It's an open-source drop-in replacement for standard linear layers. Flattening data erases spatial relationships and creates parameter overload. Consider a 4x4 feature map with 256 channels. This could be the output from a convolutional block before the classification head. During flattening, this structured grid is converted into a single vector with 4,096 values. Adjacent elements in the original grid can end up far apart in the flattened vector. Spatial relationships are completely lost and need to be relearned, even though the CNN had already captured them. Let's see how parameter explosion happens in a typical CNN. We start with a CFAR image, 32 by 32 pixels with 3 color channels. The CNN extracts features, producing 4 by 4 spatial maps with 256 channels at each location. Here's the problem. Traditional linear layers require flattening this structured data into a single vector of 4,096 values. The linear layer must then map all 4,096 features to just 10 output classes. Watch what happens to our parameter count. Over 1 million parameters. Almost all of these come from this single linear layer, a massive inefficiency that hurts both performance and memory usage. Here's how NdLinear solves these problems with a simple transformation. Instead of flattening and then applying a linear layer, we replace both steps with a single NdLinear operation. It's a one-line code change. NdLinear eliminates the need for flattening entirely. It operates directly on the structured 4 by 4 by 256 feature map, preserving its spatial organization. Instead of learning one massive transformation, NdLinear learns 3 smaller ones, one for each dimension of the image. We've reduced the number of parameters from over 1 million to just 65,000, a 16-fold reduction while maintaining the exact output dimensions. Both problems are solved. Spatial structure is preserved, and we've dramatically reduced the parameter count, all with a simple drop-in replacement. NdLinear transforms each dimension independently, rather than mixing everything. In the example of the image, height, width, and color channel dimensions carry essential structural information about the data. This approach fundamentally changes how we count parameters. Traditional linear layers require multiplying all input dimensions by all output dimensions. NdLinear only needs to add the individual dimension transformations. Multiplication becomes addition, resulting in significant parameter reductions, while maintaining the same computational complexity. The result is a transformed tensor that maintains the same structural organization as the input, but with new representations along each axis. These advantages make NdLinear a powerful alternative to traditional linear layers. Visit our GitHub repository to explore the code, documentation, and examples. NdLinear represents a fundamental shift toward more efficient, structure-aware neural architectures.